This is an HP 432A power meter. This measures RF power of different type of RF devices, and it will measure from 10 microwatts to 10 milliwatts, and it'll measure frequencies from 10 megahertz to 18 gigahertz, and it has an accuracy of 1% full scale, which is fairly good for an analog meter. Of course, there's different ways of measuring RF. You can measure the RF voltage, and then you can calculate your power, P equals E squared over R. Or you can use a thermocouple, which, in the past you could get thermocouple ammeters, that would measure RF power by the amount of heating of a thermocouple, and of course then they generate a voltage which could be calibrated in power. This particular device uses thermistors, and it's kind of a neat arrangement how they do it here. But anyway, I picked this one up at a Hamfest a while back, and not sure if it works or not. Of course, I have a theory about buying from Hamfest. A lot of the people that watch my videos are ham operators, and of course they go to Hamfest and buy a lot of things at the Hamfest. And over the years I've noticed different responses when you ask people, if a piece of equipment works or not. And I've come up with some percentages that seem to hold true when you're asking people about if their device operates or not. So normally, if you ask somebody, does it work? And if they come up with an answer of, oh yeah, it works great, I tested it this morning, works great, then you got probably about a 50% chance that the thing will actually work when you get it home. Then if you ask another guy, you say, hey, does it work? And he says, oh, it worked great last time I used it. Well, then you can figure you got about a 20 or 30% chance that it's going to work when you get it home. And then you ask a good guy, and I asked this guy, does this thing work? He was honest. He said he didn't know. And usually when they say they don't know, it's got about a 0% chance that it's going to work. But maybe we'll get lucky with this one. You never know. One of the main reasons I bought this one is because it came with the cable to connect the thermistor mount, and it came with the actual thermistor mount. In this case, the HP 8478B. Now this one will measure from 10 megahertz to 18 gigahertz, which is a pretty wide band here. And it's pretty neat how they do it. Inside of this thermistor mount are two thermistors. One of them is connected, and it will heat up when you apply RF power. It will heat up that thermistor, and of course that will decrease its resistance. But then it's got another one that is exposed to ambient air, and they're isolated. So wherever you use this thing, they're going to track with the ambient air temperature. Now, if you didn't do that and you just use one thermistor, this amplitude would vary with ambient temperature, which wouldn't be any good. So it's kind of neat how Hewlett Packard, how they devised this thing to do that. And if you want to see the schematic, I'll do a brief description at the end of the video of how this thing operates. Pretty unique. HP had some pretty great engineers back in the day. So anyway, I brought this home, and it passed the rattle test. There's nothing rattling, which is always good. But I'm going to take it apart, and I'm going to measure the power supply for voltages and ripple on the power supplies, because this thing's getting pretty old, and then we'll run some further tests on it. So I will do that next, so stand by. Now if you find one of these at a Hamfest, of course like I say, try to get it with the cable and the thermistor mount. But something else you probably should do is try to find out if the thermistors have been blown inside of the head here. There's two thermistors. And if you look at this bottom here, the pin arrangement, This is pin 3 and this is pin 4. And this is pin 1 and pin 2. If you measure the resistance between pin 1 and 2, you should be getting about 5 or 6 k ohm. If you measure between 3 and 4, you should be getting about the same. And of course they're matched, they should be exactly the same. So what I'm going to do, if I was at a ham fest, I would go in with an ohm meter, and that's not going to hurt them. These put out very little power. I'm going to measure between 3 and 4. Okay, I get about 5.6 k ohms, and that's good. So now I'm going to measure between pins 1 and 2, and I should get the same resistance reading. And if I do, that's a good indication that the thermistors are good. .5 pretty close. Okay, so I've determined that the two thermistors are intact, so that's a good sign. And then of course this connects to the cable, and you're ready to take your measurements. So if you get at the Hamfest and you get one of those thermistor mounts and they measure open circuit, you might want to just forget it because it's no good. Anyway, that's just a tip. Before I get along too far here, I'm going to check the power supply out. Got a schematic here, so I should get 7 volts, plus 7 volts. Okay, there's plus 7 volts. We got plus 7 volts, and I'm looking for minus 13, which I can catch up here. I got minus 12.5. So those voltages are within tolerance, which is good. I'm also measuring, there's a bridge rectifier here, and then there's a main filter cap here. This is 100 microfarads. So I'm measuring the ripple on the positive end of that cap. And looking at the ripple here on the scope, this is on 5 millivolt scale. It's pretty clean signal. There's a 20 millivolt scale. The ripple's almost imperceptible. So it looks like the power supply is good. So I'm going to go to the next step, which will be to hook up the bolometer, the thermistor mount, and we'll see if we can calibrate the thing. And once I do that, I'm going to run some input RF into it, and we'll see what we get. So hang on, stand by for that. I've mounted the thermistor mount to the cable and the cable to the instrument, and to set it up, this is the '8478B thermistor mount, which is a 200 ohm setting on the machine here, so I'll set that to 200. It's also got 100. I believe that's for a waveguide mount, which is 100 ohms. Then if you look on here, there's a calibration factor. There's a chart, and it goes from basically 10 megahertz to 18 gigahertz, and it shows that as you go up in frequency, the calibration factor decreases. So up near the top here, I'm going to set it up for the high end here, probably 98 or whatever. When I pick a frequency to put in this thing, I'll readjust the calibration factor. Anyway, I'm going to turn the power on now. And according to the instruction manual, what you do is you put the selector range switch here on course 0, and then you want to set the needle to 0. Of course, you do the mechanical adjustment first. I did that earlier. So then you should be able to set this to 0 with the course 0 pot. It's jumping around a little bit. It hasn't been used in a while. It may be a little dirty here, so let's exercise it. That looks pretty close. And then according to the instructions, you set your range switch to wherever you want it, and then there's a fine 0 that you push, and this zeroes out your fine 0 here. So now it should be ready to take a measurement. Hopefully we'll get something coming in here. I'm probably going to use this on transmitters. Of course, you can't connect this up. You'd blow the transmitters up. So what you need to do is connect something like a, well, here's a 50 watt 20 dB attenuator. And what I can do is I can connect this to the thermistor like that. And then I've got 20 dB. So I'll drop whatever signal's coming in here, I'll drop it 100 times before it goes in. And then if I want to, I can also connect, here's a variable attenuator, an HP 355D. This is adjustable, and I can adjust this from basically 0 dB up to, well, 120. And there'll be a, actually I'd want to connect, it's got BNC, I'd have to adapt it. I'd want to connect this here and then this to the transmitter. So I drop most of my signal in here. And then if I set this 20 dB, if I set this to 10 dB, that would give me 30 dB. That would be 1,000. So I could put in, you know, a couple watts, and that would only give me a few milliwatts. So I think that'll be the next step. But I think first I'm just going to connect this up to a generator, and I can generate directly a small enough level where I won't hurt the meter. So I'll have to do that on the other bench, so I'll set that up and then be back for that next. Stand by. I have the HP 432A power meter set up here to test it. I've got a total of 30 dB of attenuation. This is a 20 dB 50 watt attenuator, and this is a 10 dB attenuator. So it's a total of 30 dB, which will divide the signal coming in here by 1,000. So here is a HTX 404 on 440.5, and I'm going to put out a couple watts from that. And so this attenuator setup should reduce that by about 1,000, 30 dB, 1,000, which should give us about 2 milliwatts on the meter. And I've got it on 3 milliwatts full scale. So here's 3, here's 2. So it's going to be somewhere around here will be, if it's working, that is. Maybe we'll get lucky. Sometimes you do. Anyway, before I connect it up to the 432A, I'm going to transmit into my Boonton microwatt. This is a model 42A here. So anyway, here's the HT. I'm running through a watt meter here, and then through the attenuator setup into the microwatt. So when I hit transmit, this shows about 2 watts, and the microwatt on the 10 milliwatt scale is showing slightly more than 2 watts. You can see right here. So we've confirmed we've got about 2 watts. That is a little bit more than what's showing up on this MFJ meter, which who knows. But anyway, the next step will be to connect the HTX 404 to the 432A. So we'll do that now. And here's the thermistor mount here. This is the 8478B. So I'll connect that to the series connected attenuators, which will reduce my signal by 1,000. Always want to use attenuators. You'll blow these meters up if you transmit in them. I've already gone through the calibration of the 432A. It's on the 3 milliwatt full scale, so this would be 3 milliwatts, 2 milliwatts, 1 milliwatt. So now I'm going to hit transmit. And we're showing just slightly more than 2 milliwatts on the meter here. And this one, the 432A, is showing just under 3 milliwatts. About 2.8 milliwatts, it looks like, allowing for parallax. So the barometer, the thermistor mount here is working. A little bit of discrepancy here between the microwatt, which is just above 2, and this one. And of course these two are, I have more confidence in these two meters than this one for accuracy. In fact, measuring at the lower part of an analog meter isn't the most accurate. You always want to measure in the upper 2/3 if you can. So anyway, this is working here. So what I'd like to do to calibrate this, I'm going to find somebody that has an accurate standard I can calibrate this against, and then I can use this to calibrate all my other instruments, including different watt meters, this microwatt meter, etc. So anyway, if you see one of these at a hamfest, you might want to pick one up. They're real handy to have and highly accurate too. And with a set of attenuators, you can measure just about any power you want. You know, I've got 30 dB here, which will divide the power by 1,000. You could go up 40 dB. That would be divided by 10,000. As long as you got enough power dissipation. This is a 50 watt attenuator. So anyway, if you pick one of these up, try to get the cable and the barometer head, the thermistor head here, because without those, this basically is useless. This will be a brief description of the circuit operation of the 432A power meter here. This is a schematic of the A1 module in the unit here. And to the left of this dotted line, this is in the thermistor mount here. There's two thermistors, one up here. This is the one that measures the incoming RF power, and the thermistor on the bottom here is used to measure ambient temperature here. And the reason they do this is that as you use this device here, as the ambient temperature in the room that you're using it varies, these two thermistors will both vary equally. They're matched thermistors, and as the temperature rises and decreases, these are negative temperature coefficient thermistors, their resistance will change equally. So this thermistor on the bottom is affected by ambient temperature only, and the thermistor on the top, you can see the RF coming in here. This thermistor will be changed, its resistance will be changed by not only ambient temperature but also by heating from the RF input applied here. They're thermally isolated here. Now the two bridges here are fed with a current source over here. The top bridge, the RF thermistor bridge, is driven by Q11 here, and the bottom thermistor is driven by Q6. And all of this circuitry here, all this does is maintains a balance in the bridge. In other words, as these resistances change, it will change the bias voltage on each bridge circuit to maintain a similar output. So when you first set this device up, you're not applying any RF. You adjust the course 0 here to balance the bridge. So with the bridge balanced, the outputs will be the same. Now when you apply RF, that will tend to unbalance the bridge, because this thermistor is heating up, its resistance will decrease. So then this, to maintain the balance, this feedback system here, which is these differential amplifiers, this will change the voltage at the top of the bridge here to maintain that common resistance between the two. So then this voltage will actually change here. So the reason they do that is it balances out any changes in ambient temperature, so that you're only going to measure the change due to the RF into this thermistor here. So now with the bridge balanced here, initially before applying RF power, you've got two outputs here from this assembly. You've got the VRF output signal here and the V compensation signal here, and they'll be equal. When you apply RF here, it will start heating up this thermistor. That'll unbalance the bridge, and since that's going to change the biasing into that bridge circuit here, that output voltage is going to vary. So now VRF here, the output signal here, is going to vary with the amount of RF coming in. And these two signals here are going to be applied to the meter logic circuit, which is on another board here. Here's a diagram of the meter logic assembly here, and on the left side here you can see the VRF signal and the V comp signal are applied here to this assembly. The function of the meter logic assembly is to take the two signals from the bridge assembly and to produce a V comp minus Vref and a V comp plus Vref, and they do that by applying the signals first to this chopper here that's driven by a 5 kilohertz multivibrator here. It's kind of nice to see where HP isn't using a synchronous motor, incandescent bulbs, and light dependent resistors like some of their earlier devices. But anyway, this signal drives this chopper, and what the chopper does is it produces a square wave signal. The amplitude of that square wave signal is proportional to V comp minus Vref. The output of the chopper is applied to the range amplifier here, and of course you've got your range switches which vary the gain of that circuit, and then that's applied to the calibration amplifier here, whose gain is dependent upon these calibration factors, which vary with the calibration factor for the individual thermistor mount that you have. So you've got that adjustment. It's a front panel adjustment here. Now to produce the V comp plus VRF signal, they're summed together. Here's where they come in on the left here. They're summed together here to these two 10K resistors, and they're applied up here to a voltage to time converter. This is also driven by this 5 kilohertz multivibrator here that's produced by Q23 and 22. The voltage to time converter produces an output pulse signal whose amplitude is proportional to the sum of V comp plus VRF, and that output is fed here to the electronic switch. The output of the electronic switch here produces 5 kilohertz pulses. The amplitude is proportional to V comp minus VRF, and the width is proportional to V comp plus VRF. And the output here is fed into the metering circuit. And then on the right side here at the upper right, that signal is fed to the meter, which is calibrated in power. You've got a capacitor across it which integrates those pulses to feed the meter here, M1. So it's interesting, the purpose of all of this discrete circuitry here is to provide a stable output in the meter here that only varies with RF input to the device. It doesn't vary with ambient temperature changes. And it does that through a feedback system. and it uses that feedback to keep the bridge balanced in deriving the output that's measured on the meter here. It's a lot different way than they do it today, but this is how they did it back in the old days. And it's interesting here, you've got discrete transistors here to produce the 5 kilohertz signal. Anyway, that's just a brief review of the circuitry in the HP 432A power meter. That was a brief review of the Hewlett Packard 432A power meter. So I hope you enjoyed that, and if you see one of these at a Hamfest and you can get the thermistor mount with it, pick it up. They're really nice units. It's old technology, but it's still a very useful addition to your electronics lab. Anyway, thanks for watching, and we'll see you in the next one. Bye for now.